G'day folks, nothing warms my heart more than when my students are working and asking me questions. So I got a question this morning asking about some of the parametric equations that I spoke about for the Extension 1 course. So we're jumping in Cambridge 5, oh goodness me, I don't, the exercise has lost me, but it's the parametric equation. I think it's 5H. Question 3 we're looking at. It says to show that the point CP and C on P lies on the hyperbola xy equals c squared. Okay, so how do we do things like this? Well, look what it's saying. It's telling us that x is equal to CP and that y is equal to C on P. Well, that's a pair of simultaneous equations. Now, they want us to get this equation in terms of x, y, and c. In other words, they've eliminated p. There's no p here. There's p is there. There's no p here. So they've eliminated the parameter p. Well, how do we do that? Let's eliminate like we normally do in simultaneous equations. So I'm going to start by numbering my equations. And then I think that it's pretty obvious that from equation 1 I can make p the subject relatively easily. So I'm going to say from equation 1, p is equal to x on c. And that's, I'm going to call that 1.1 because it's equation 1 modified, right? So what I'm going to do now is I'm going to substitute 1.1 into 2. And so wherever I see a p in equation 2, I'm going to write x on c. Well, equation 2 says that y is c over p, but p now is x on c. Look at this, I'm dividing by a fraction. When I divide by a fraction, I invert and multiply. Okay, over here I'm dividing by x. I don't want to divide by x, so I'm going to multiply x over to the left-hand side. So I get xy equals c times c is c squared. That's what they asked me to find. Okay. Part B says to complete the table of values below or to complete the table of values for x equals 2p and y equals 2 on p. Well, they start at -3, -2, etc. I'm only going to do the first couple because it's just mechanical, processing numbers from here. So if x equals, I'll make that a bit clearer. If x equals -3, well then 2p is, if p, forgive me, if p equals -3, if p is -3, then 2p is -6. If p is -3, then 2 on p is -2/3. If p is -2, then 2p is -4. 2 on p is -1. Okay, you keep on going. You're going to end up getting values for p I'll leave you to do that part. That's actually a pretty simple exercise. I'll let you go. Part C says what happens as p approaches infinity. What happens as p approaches infinity or negative infinity? Or 0 from above or 0 from below. So this notation, p approaches 0, with a plus sign means that P gets closer to 0 from above, and this P with a minus sign, P gets close to 0 from below. Look, we know that if xy equals some number squared, it's going to give us a rectangular hyperbola. We spoke about rectangular hyperbolas already. We know what the graphs for those look like. And you're going to have your table of values that's going to help you out with that as well. So what we're looking at is that curve there. Very easy to draw with your math aid. And we're asked, what happens as P gets really big? Well, as P gets really big, X gets really small. Okay, so the further we move out, the lower this value of X gets. X approaches 0. Oh, sorry, forgive me. As P gets really big, X gets really big, but Y gets really small. Forgive me, I misspoke. Okay, remember that this guy here is our X value, this guy here is our Y value. So as P gets massive, as P approaches infinity, and you'll see it from the table that you draw when you complete all the values, as P gets bigger and bigger, that'll make X get bigger and bigger, but the Y value will get smaller and smaller. You'll see that when you complete the table. And you can see it from the graph as well. So P gets bigger, that means X gets bigger. As X gets bigger, Y gets smaller. What happens as P approaches negative infinity? Well, as P gets to negative infinity, well, then X gets more and more negative, increasingly negative. And you see what happens to Y. Y will approach 0 from below. So let's give a little bit more detail. As P approaches infinity, X approaches infinity, and Y approaches 0 from above. As P approaches infinity, X approaches infinity, and Y approaches 0 from above. As P approaches negative infinity, well, then X approaches negative infinity, and Y approaches 0 from below. As P approaches 0 from above, in other words, as these values get smaller and smaller on the positive side, well, then X approaches 0 from above, and Y approaches infinity. Y gets bigger and bigger. Okay. As P approaches 0 from below, in other words, as our X values start to creep along here, X gets closer and closer to 0 from below, like from the negative side. X approaches 0 from below, and Y approaches negative infinity. Y gets lower and lower. Okay. So that's all of question 4. All of question 3 there. I'm going to do question 4 as well, because it's a different kind of a function. So it's not a hyperbola. This time it's going to be an ellipse. Don't panic. Don't think, I've never seen an ellipse before. We're just interested in how parametric equations work. And what we're doing is we're going from a parametric representation to what's called a Cartesian. So you probably think, oh, what does that mean? Again, don't panic. Mathematicians love to throw words around that make them, sound really smart to everybody else. Cartesian just means a normal XY equation. Okay. So let's have a look at question 4. It gives us A cos theta, B sin theta. And it wants us to show that that's on an ellipse. And then, so we don't have to
stress ourselves out and wonder what the equation of ellipse is. They tell us the equation of the ellipse is x squared on a squared plus y squared on b squared equals 1. Okay, so what do we do? Well, we do exactly what we did last time. Last time we started off with x equals the x coordinates with the parameter, a cos theta, y is b sine theta. And now they want us to eliminate, so we've got an x, an a and a theta, a y, a b and a theta. Over here we've got x's and a's and y's and b's and no thetas. So we need to eliminate theta from this thing. There's a trick to eliminating theta when you've got sine and cos. It uses a result called the Pythagorean Identity. What's the Pythagorean Identity? It's one of those scary things that it's a label that mathematicians give to things to make them sound smart. Don't panic. The Pythagorean Identity says that sine squared theta plus cos squared theta equals 1. Okay, it's given to you on your reference sheet, but it's a good one to know anyway. So it's not one you should need to be going to look up. So sine squared theta plus cos squared theta equals 1. Well, how does that help me? Well, okay, if that's equation 1 and that's equation 2, well, I can square equation 1 and I can square equation 2 to say that x squared equals a squared cos squared theta. And equation 2, I can say is y squared equals b squared sine squared theta, and call that 2.1. Now, why did I do that? Well, I did it because I want to get rid of theta, and I need a sine squared and a cos squared because they very, very nicely just disappear off into a 1. So look, from equation 1, can you see, or 1.1, can you see that I can get a cos squared if I divide by a squared? And from equation 2.1, can you see that I get a sine squared if I divide by b squared? So I could get x squared over a squared equals cos squared theta. Call that equation 1.2 because it's equation 1.1 that I've modified again. And I can get a y squared over b squared equals sine squared theta. Call that equation 2.2 because it's equation 2.1 that I've modified a bit. Now, if I add these two equations, if I add the equations together, well, I get x squared on a squared plus y squared on b squared. Equals sine squared theta plus cos squared theta. But what's sine squared theta plus cos squared theta? According to the Pythagorean identity, it's 1. And that's what we had to prove. Okay. Then they get you to go through a similar exercise where they give you some values that they want you to put into a table. I'll leave you to do that because it's just basically some calculator work. And then they say sketch the curve and state its equation. Let me give you a little bit of a heads up. If you're thinking about, any of you guys are thinking about extension 2, they've taken conic sections out of the syllabus, but that doesn't mean they can't try to squeeze them in somehow, somewhere. So it's a good idea for you guys to understand some basics about ellipses. Not hard, very, very easy, I promise you, so don't panic. Let me explain that now, just in case you come across any ellipse work later on, okay? And you'll see a lot of ellipse work in older HSC papers if you look at extension or conic sections work. You'll see a lot about ellipses if you look at older HSC papers. And you're just curious, want to know how they go down, right? So, what's an ellipse? An ellipse is an eccentric circle. Oh gosh, how do you make a circle eccentric? Well, how do you make a person eccentric? You know, I'm not eccentric, I'm perfectly normal. But let's say that I was going to be a little bit eccentric. I'd have to do something eccentric.
You know, like, I mean, if I was to sort of like lean over, that'd be an eccentric thing to do. Like, it's a bit sort of out of the ordinary. Okay. It's exactly the same with a circle. Now, I just so happen to have a little jar of my my infusions here, so that's a good little resource for us. See that's a circle. When you look at it, you see a circle. But if I was to tilt my circle and make it a bit more eccentric, I can't actually, I'm confusing my left and my right now. If I was to tilt that circle, just look at the top. The top doesn't look circular to you anymore, does it? It's been squished down. So when it was like this, the height of my circle was that high. So I'm going to leave those fingers at that height. When I tilted my circle, well, what's the height of it now? Well, the height's considerably smaller. Okay, if I have that finger there and that finger there, that's considerably smaller than it was. Whoop, got to open it up, close it down. Okay, this way, that axis hasn't changed at all, but the vertical axis has. So an ellipse is a circle that's been tilted, and the more it tilts, we say the more eccentric it is, and the less it tilts, we say the less eccentric it is. Okay, so there's a formula. There's actually a mathematical formula for eccentricity. I'm not going to burden you with it now. Wait until you're working on that stuff in some extension 2 work. When we look at the ellipse, we can't speak about when we look at our circle, we can speak about a diameter. Okay, but when we talk about the ellipse, well, we can't really talk about a diameter now because what are you going to take as the diameter? That guy or this guy? You know, what exactly has gone on here? So instead, we talk about a major axis and a minor axis. Okay, so that's what we call that the minor axis, and we call that the major axis. So we call this here, because we're really creative, the semi-major axis, because it's half of the major axis. And we call that guy there the semi-minor axis, because it's half of the minor axis. And it turns out, you can do a little bit of algebra to verify this, that A there is my semi-major axis, and that B there is my semi-minor axis. Okay, so when you look at question 4, B, part 2, you've now got a very big leg up to do that. Let me know if there's any more questions I can help with, guys. Take care.